Okay, can you hear me? Okay, fine. Hello, everybody, and thanks for coming to my speech. I am Giulia Menichini, and today we are going to talk about 3D on mobile platforms, specifically the Unity platform. These are my contacts. I am from Netfarm, that is an Italian-based company. And okay, so let's begin our introduction. Okay. Okay, about 3D and mobile, we are talking about 3D-based games. They are quite popular right now. They have a good look and feel, visual impact. They are easy to play. Every one of us has its own little pastime just to kill the long hours waiting, be it a card game or a point-and-click game or a gestional game or an FPS, etc., etc. But what if, in our case, we want us to engage into the simulation something complex, something that is quite different from the standard mobile games, be it in an Android or iOS environment? Okay, let's have a brief introduction of what it means to build a simulation software. Developing a simulation software is not only coding at all. Developers, before putting their heads on the code, must dig deep into the theory of the model they're trying to represent to avoid potential incorrectness in the final results. Well, without entering too much in detail, we can summarize the necessary long process to build a simulation software in 7 steps. The first step is the problem formulation. It's easier to be said than done because we need to focus clearly on what we want to simulate. When a simulation study is firstly initiated, the exact problem to be solved is not precisely stated or even completely understood. Thus, as the investigation proceeds and a better understanding of the general problem is obtained, the exact thing to simulate, the exact scope of our simulation may be reformulated even several times. The second step, information collection. Once we focused on the scope of our simulation, we need to collect as much information as possible about our system. We need to have an understanding as precise as possible about our system, the dynamics, the formulas, graphs, etc., etc., to decide what to include and what to exclude from the system in the next step. The next step is the assumptions phase. Well, a simulation model should be an abstraction or a simplification of the real system, with just enough detail to answer the scope of our simulation. This phase should be conducted with care, because we do not want to miss important parts that can be vital to the results of our simulation. Then we come to the program model, at least we come to code. This is when you scout the best possible technologies to see what is the best fit for your simulation. And then you can implement in practice by coding or by using a framework all the paperwork you just produced. The validation phase, the fifth phase, okay. In the validation phase, you compare the performance measures from your model, for the model you just programmed, with the measures collected from the actual existing system. In this phase, we can verify if the assumptions we made in the third step, here, were correct, or if we have to simplify or go deeper in detail about our model. Then, the experimentation phase, the actual using of our simulation framework. In this phase, we usually decide on tactical issues such as the length of the warm-up period, that is the starting period in which our simulations take place. So the warm-up period is generally the period in which we have to wait to reach a steady state. to reach the steady state to effectively start your collecting your results. And then number of simulations, etc., etc. After you've done all of this, we come to the documentation phase, in which we have to collect documentation about what we have done, the conceptual model, detailed descriptions of the computer program with associated tools, libraries, code, etc., etc., and the results conclusions, of course. So, in our case, for the sake of simplicity, we can assume we already started the model, collected information, made the necessary assumption, cut out what it wasn't necessary, and then we can come directly to the program phase, the fourth phase, sorry. Okay, our case study, it was a simulator of the effects of electromagnetic fields on an urban environment, in close collaboration with Pisa University, that is very close to our offices. We collected information about the physics of the systems, graphs, equations, as I said before. We made the necessary assumptions, as I said, to avoid overcomplicating the model with unnecessary information. And then we ask ourselves, what simulation framework should we use? What tool should we prefer to effectively put in practice all the paperwork we just collected? Okay, our choice fell on the Unity platform for a good number of reasons. Okay, let's highlight the main characteristic of the platforms. Well, the Unity platform is a game engine developed by Unity Technology. It's a cross-platform game engine. That means you can develop lots of games for different platforms, and you can develop both 2D and 3D games. Notable examples of supported platform by Unity are Android and iOS, of course, any desktop operating system, consoles like Nintendo Switch, Xbox One, and even augmented reality platform like Steam VR and Oculus Rift, for instance. Okay, so the primary scripting API is in C#. That is the official supported scripted language. It previously supported Brew, that was removed in Unity 5, and the Unity script, that is a slightly modified version of JavaScript. That it was deprecated in one of the latest releases. I don't remember exactly which one, but one of the 2017 ones. And you can see an example of the C# effectively used in Unity, that has a bit more data structures suitable for our purposes. Okay, as I said before, we chose Unity because it is cross-platform. It means that we can develop software for both desktop and Android and iOS platforms. It has a big supportive community ready to help you. There's plenty of documentation and with examples about the platform, and this is very, very easy to use, even for amateurs that want to develop their own indie little game, and developers who struggle to move the first steps in the world of 3D platforms, as I was. Okay. Forgot to mention, all these 3 games that you saw a screen of them before were developed using the Unity platform, but there's so much more, so many games developed with this platform. And do a bit of research, and you find it really astonishing how many games are developed in Unity. Okay, so let's take a look to the UI elements of Unity. Okay, there is the scene view. The scene view is where we build our game, and it can be easily called the heart of Unity. It allows us to view and interact with the elements present in the scene. Okay, as you can see here, there are several elements that can help you moving around your scene. There is the grid that can help you moving into the plane and understanding where to put your elements. The gizmos are anything that doesn't have a physical representation, like for instance the light and the camera, and can be visible and turned on and off via this small interface in the scene view. And then there is the 3-axis gizmo, that is little nice utility that allows you to see your game from a different point of view. By clicking on one of the 3 axes, the camera shifts accordingly to let you see your game from different point of views. Okay, so the project window. The project window is when Unity displays the assets and files we have available, giving easy access to them. Examples of files include script files, textures, material files, audio files, etc., etc. Also, the current scene and the other scenes, the other scenes are present in this section. Then, the game view. The game view is where you can have a quick preview of your game whenever you want, just by hitting the play button, and you can see a video about that. You can just play and stop your video wherever you want. Okay, it's the play button, and you can see a preview of what your game will look like. You can play with controls, etc., etc. Okay. You can stop the preview anytime you want, because maybe you want to check how the information progresses in our scene. Okay. And these are the play mode controls in which you can control the preview of your game. Okay. Sorry, I have technical difficulties. Okay, the inspector window. The inspector window is where you can show properties of the selected objects or asset. We can see about that what we mean by this. But for now, this is the window you can consult to see the details of the object present in your scene. And then the hierarchy windows, last but not least. It is the window in which elements present in the scene are shown. You can see that Unity supports a hierarchy of objects. That means that objects can be rearranged into groups to sort and coordinate their behavior in various ways. We can see a nice example here of what I was talking about, the canvas object. The canvas object is, roughly speaking, where you can put and manage all the UI of your game. You can see what in 2 dimensions your game will look like by hitting this small button here. You can switch from the 2D to the 3D perspective. And okay. So in this UI, you can see we inserted a panel result view, as a panel result object, just to display some details to the user about objects he's selecting. And you can see that by changing the properties of the parent objects, even the child object will change the properties, and all the view will move accordingly. Okay, so let's look to some basic concepts about developing environments with Unity. The scene. Okay, the scene is where you put your objects, and you can play with them, move them, change the properties, see the details, etc., etc. The game object. The game objects are the elements that compose your Unity scenes. You can see a simple cube example here with the inspector view open that shows you the details of your objects. And almost everything in Unity is a game object. Physical representations of enemies, sprites, trees, etc., etc. Even the camera and the light that illuminates your scene are game objects. Game objects are made of various components. Let's see here a short summary of the most important components of a game object. Okay, the transform component, it is mandatory for every game object. It describes its position, rotation, scale, etc., etc. It describes the position of the object in the scene. The collider component handles physical collisions between objects and interactions such as the mouse button, the touch input, etc., etc. And often the collider component, it doesn't need to be the exact same shape of the object, but very often a simple hitbox that is a cube surrounding the object, it is necessary and even recommended for performance, for avoiding performance issues. Another very important component is the script. Any file or piece of code that describes the behavior of the object is considered a component. And then the material that handles the look and feel of our object. We will talk about it later. Okay, so in this video you can see that you can add the script that modify the behavior of your components by simply dragging and dropping them from the, by simply dragging and dropping them into the component of interest. We have our joystick component here, and we want to add a script to the component that specifies its behavior. So we go into the script folder in the project window. We select the virtual joystick component, and we simply drag it into the parent object of the joystick. And you can see here in the inspector window that it has been added as a component that describes the behavior of the UI object. Okay. Sorry, I have technical difficulties. Okay, here we are. Okay. Then the camera object. The camera object is as I said before, is a game object tool, a game object tool, and it displays the content of the scene to the user. As you can see here in the camera preview shows you how the scene will look like from the point of view of the main camera. You can add as many cameras to your scene as you want, but it is mandatory that every scene has at least one camera. The camera is an interesting object because depending on what type of camera you choose, you can develop really any game you want. For instance, for a puzzle game, you will need a static camera that will show the full view of the puzzle all the time. For a first-person shooter, you want to parent the camera to the player character and place it at the character's eye level. And for a racing game, you would probably like to have the camera follow your player vehicle, and so on. With creativity, you can develop your own behavior. Okay, prefabs. Prefabs can be described as pre-made game objects that you can instantiate anytime you want in the scene. You can use them really for a variety of purposes, to create a set of enemies or sprites, as I said before, background elements, etc., etc. It acts as a template here, as a template from which you can create new object instances in the scene. What's more interesting that any modification to a prefab reflects on the object in the scenes as well. Okay, so we have another video here about how to create a prefab and use it effectively to instantiate a specific set of objects. We have our sphere objects here, And then we go into the prefab folder, and we create a prefab that we decide to call my prefab. Okay, so we drag the game object in our scene here to the my prefab, and boom, we have our little objects, our little standard object, with all the parameters that passed from the sphere object to the prefab prefab. Okay, we just modify the scale of the object, and you can see, but simply by drag and drop it into the scene, you can instantiate as much instances of it as you want in your scene. Okay, with of course all the same properties of the sphere objects. Okay, let's talk a bit about materials here. Materials play an essential part in defining how your object is displayed. They are essentially wrappers which contain a shader and the values for its properties. Different materials can of course share the same shader and can be different in only small parameters, like the albedo is in this example here. It's exactly the same material but with a different albedo. So, what is a shader? Shaders are mathematical models that tell the graphics card how to render a 3D object on the screen. They describe essentially how and if the object receives light, what color it has, if it's shiny, opaque, they regulate the shadowing of the object, etc. etc. Unity supports two very different types of techniques of shader generations, the surface shader and the vertex and fragment shader. Surface shader is the most intuitive way to create a shader because it hides the calculation on how light is reflected and allows to specify intuitive properties such as the albedo, the normals, etc., etc., without tinkering with the low-level implementation of it. The vertex and fragment shader, opposed to it, work close to the way the GPU renders triangles and have no built-in concept of how light should behave. Shader programs written this way are more flexible, and you can create the effect you need. Even surface shaders are converted into a bunch of vertex and fragment shaders, but that comes at a price. You have to write more code, and it's really a lot harder to make it interact with lighting just by hand. Okay, the touch inputs. Unity supports a very wide range of inputs, such as the mouse inputs, the touch inputs for mobile platforms, and any other type of inputs that is compatible with the supported platforms. In this case, regardless of the platform, that's what it is interesting in my opinion. All the touches that at a certain point are active on our device are stored in an array called touches. Touches, the input.touches. You can just retrieve them using the input class. And every single element of the touches array can store useful information as, for instance, the on-screen position, the touch phase, started when taken, etc., etc., the number of the finger that is producing the touch. The length of the touches array can tell you how many fingers are present in the scene in that very moment, and you can inspect every touch of it and retrieve this useful information for your purposes. You can see here this little snippet that it is attached to the camera of a scene that handles the behavior of the camera depending on the number of touches that are present in the screen at that moment. For instance, if there only one touch, you rotate the camera accordingly without, we don't go into the detail of the implementation of the methods. Or if there are two inputs, you can implement the pinch to zoom feature and so on. Okay, the build process. Let's see how we can deploy effectively our software in our selected platform. Okay, this is the build setting window in which you can set your build process, including the target platform here, and the scenes you want in your build. You can fully customize the scenes you want in your build by simply dragging and dropping them from the scene to this panel, so that maybe you want a different scene for a different platform, or you want more or less scenes in your platform, in a different platform of choice. Then, as I said, there is the platform choice here in this panel, and the setting specific for each platform. This is the PC, Mac, and Linux set. These are the PC, Mac, and Linux settings. Okay. So, the Android build process. In the Android build process, you can select if you want your build to be debug build or release build. You can also attach your very own debugger here. You can select this tick box to attach your debugger to debug effectively your scenes, and you can choose you can build directly the APK and then deploy it via ADB, or just you can build the APK, but you can deploy it immediately on your Android phone. The iOS build is more or less the same, but it is a two-step process. The settings are essentially the same, but it is a two-step process in which the Xcode project is generated by Unity, and the Xcode project is built by Xcode and deployed at one on the actual device. Okay, so these are the player settings. Another important type of settings in our Unity build that allows you to set various options for the final game. Okay, as you can see here, there's a settings. There are platform specific or general settings like the company name, the product name, the icon, the default icon, and the default cursor. Then you can choose the icon and other settings, the resolution and presentation, the standard orientation of your game. Okay. So the splash image you want to be presented in your game, and what's interesting is that these options is grayed out because. If you're using a free license of Unity, Unity forces a splash screen to your game that you can't remove it unless you pay for a better subscription. Okay. Then, after we had this little introduction to the Unity platform, let's get to our case study. Okay, our case study, as I said before, was a simulator of electromagnetic fields in urban environments, and we chose to bring to you the island of Gorgona, that is a small island in the Tuscan archipelago. And okay, each of this scenario, and also the Gorgona scenario, was built starting from a file DXF. The DXF file format is a particular file format developed by Autodesk to be run and imported from and into their software AutoCAD. It is an open source file. The specification for this format are freely available on their website, and there is a lot of tools, even online, even on the Autodesk website, that allow you to see the XF files. Okay, you can see here. You can see here a template of what the XF file looks like. It's just a plain text files organized with these keywords in section and headers. The header section contains all the necessary variables that are needed to define your file, and each section starts with the XF tag 0 section, and it ends with the XF tag end section. The end of file tag signals the end of file. We are particularly interested in entities that represent the graphics of our objects. Each entity contains standard information such as color, layer, line style, and geometries, as well as a number of attributes specific to its entity type. For example, all the 2D entities have thickness, while the text entities have fields for font, size, and the text string, in addition to its standard attributes. And a polyline is a particular type of entity that consists of connected straight line that can be used also for curves that are represented as a long list of connected straight lines. Okay, this is the XF file used to create our terrain for the Gorgona Islands. In this particular case, we had to deal with isocontour curves describing the structure of a terrain. So, but how did we make to generate a mesh from such a DXF file? Well, this goes deeply to mathematics, but without entering too much in detail, there is a particular algorithm called the Delonois triangulation. That is a particular way, let's say, to join a set of points to make a triangular mesh. Delonois triangulations tend to avoid producing skinny triangles, and this is very suitable for terrains. We won't cover here the details of algorithm, of course, but all you need to know is that the Delonois triangulation takes the set of points that compose your DXF file and then creates an OBJ file. That is one of the many formats supported by Unity to be inserted in your scene. Okay, another interesting thing is the height water shader that we use to color the terrain. The height water shader, it's a Weltesserfarm shader in which we set a different color for every level of the terrain, so that you can see the result in the following video. You can see here the scene, the empty scene with just the UI, and then we go to the resources folder, the prefab folder, and we just put the OBJ file from the prefab folder to the Gorgona ground parent game object. As you can see here, the terrain is completely blue because it lacks the shader that colors the terrain. So to color the terrain, we have to go to the shaders. Firstly to the shaders to see what is the shader that we want to apply to our game object. And then we go to materials, because the materials, as we said before, wraps the shader. And we just drag it into our game object, and we can see that the terrain is colored differently depending on the height of the terrain. Okay, just a quick look around. So, okay, the next one is how we generated the buildings to put in our scene. Well, the buildings were another DXF file we imported in the same way. And you can see that by going to the houses, into the houses folder, we have lots of files that represents the object of the houses of our terrain, and just by dragging them into the parent component, the Gorgona houses, it's being dragged and imported in our scene. You can see here that by selecting in our hierarchy window an object of interest, the camera zooms to that particular object, and the inspector window displays the details regarding that particular object. Okay. Another selected object here. Okay, I can present you now the final result of our software. You can see that I enabled in the debug options an option to let you see the touches. And we can see here that houses are differently colored depending on the intensity of the field, the type of field we are measuring. And by choosing a different detail on this result window, on the result panel, the houses are colored differently because of the different electromagnetic field in that particular point. These houses are full of receivers to let you see the effects of the field. Okay, transmitter and receivers, yes, because we have to put the transmitter. Okay. So that's it, I think. Okay. You can freely find a lot of documentation and tutorials about the Unity platform. In our case study, we didn't put much of a detail because it wasn't really necessary to our purposes, just like the lighting or the windows, etc., etc. But you can find pretty much anything in this type of links. Even the Unity 3D website, there are tutorials that cover in detail how to build your first games. There are assisted tutorials. And the documentation, the plain old documentation in which you can lose yourself, then Stack Overflow. I don't have to mention it. And then another very interesting with the platform is the asset store, in which you can find quite a lot of assets for free or paid to help you build your Unity game. Okay, so thank you for your attention, and that's it. Thank you very much. If you have questions. So if you don't have questions, I think we finished. No questions? Okay. Okay, I think we are done then. Okay, thank you. Thank you for coming.